Okay. Um, since it had been a couple of years since I wrote homework hints, I completely forgotten that I'd only actually written out hints for two of the problems. Um, whoops. Um, so
I'm not gonna lie, when I sent you that email, I thought I lost my mind. I was like, wait, there wasn't anything else.
yeah. So now just my memory failing me.
It's fine. I just thought I was
so
losing it.
and I have a feeling that there might not be too many people who are turning in homework to by tonight. Okay, and especially those of you who have had class from me before know very well. So for the benefit of everybody else, I really don't care. So I want to be completely honest about it, because it's not like I'm chomping at the bit to grade these things on Thursday anyway, because there's other stuff to do. Of course, if this weekend, normally I would say, okay, I'll just have grading of a homework ruin my weekend, but this weekend is Valentine's weekend, so I'm not sure how that's going to go. So, um, but I would certainly rather see something that is um, uh, late and complete um, than than negation of that. Um, so, um, if some things come up or difficulties with problems, based on questions I get that seem to be more general interest, as opposed to, hey, can you look at this code and see if it's right? Um, then I might update the hints accordingly, and if that happens, I'll let you know. Um, and we'll probably have some time at the end today for questions on the homework anyway. Okay, so in keeping with solving ax equals b, where A fits into a certain category of matrices. Last time it was banded matrices, and today it'll be symmetric matrices, and especially focusing on matrices that are symmetric, positive, definite. Now, so first with symmetric, so real matrix A is, and has to be square, and by n matrix A is symmetric if A is equal to A transpose. So in other words, reversing the sense of rows and columns leaves you the same matrix. So a quick example of, let's say, a 3 by 3. Okay. All right. So okay. So this matrix is symmetric. If you so really across the main diagonal. So entries on opposite sides of that main diagonal is like mirror images of each other. Okay. Now, so in the LU decomposition, A equals LU. For now, we won't talk about pivoting. So we know that L is unit lower triangular, U is upper triangular. So what I'm going to do is modify this decomposition a little bit so that we have a unit lower and unit upper triangular matrix. So I'm going to break U down into DM transpose, where D is diagonal, and more specifically, so each diagonal entry of D is just one of a diagonal corresponding diagonal entry of U, and M is unit lower triangular. So therefore, M transpose is going to be unit upper triangular. So how I would get M transpose, that's just equal to D inverse U. So I make D from a diagonal of U, multiply U by D inverse. That will make the diagonal entries 1, so it's unit. This is already upper triangular, so M will be unit lower triangular. So now we have this decomposition. A is equal to LD M transpose, where both L and M are unit lower triangular. Now, this is another way of looking at LU. Now, for a general system AX equals B, this decomposition is totally useless. You might as well just stick with LU. But that changes if A is symmetric. Then we have a following. If I look at the transpose, now A transpose equals A, but focusing on decomposition, remember, the transpose of a product is the product of the transposes in reverse order. So taking a transpose of this, LDM transpose, would give me M, and then D, and then L transpose. Now, there's no need to take a transpose of D because it's a diagonal matrix. The diagonal matrix is already symmetric. And that is equal to... So these two factorizations now are equal. So now what I'm going to do is M and L, they're unit lower triangular. Therefore, they're invertible. So I'm going to multiply... okay, I was going to take this part. So I'm going to multiply by M inverse on the left. Okay. And then I'm going to multiply by M inverse transpose on the right. Okay. Now I have a rather funny notation here, minus T. That's because if you take the inverse of a matrix and then take a transpose, that's the same as taking a transpose of any inverse. So it doesn't matter what order you carry those operations out in. So we have this symbol, minus T, that's inverse transpose, that encapsulates all of that. Okay. But using a product of a property of inverses and transposes, that AB transpose equals B transpose A transpose. Okay. Transpose. Then we have the following, where I can rewrite this product as... Okay, so I'm going to basically pull the transpose out, and therefore this would just become L. And then M inverse transpose would just become M inverse. But I have to change the order. Okay. So now I have M inverse L transpose over here, and then just plain M inverse L over here. Now, the left side is upper triangular. The right side is lower triangular. Because M and L are both unit lower triangular, and multiplying or inverting keeps unit lower triangularity. So, what can I say about both matrices if they're equal to each other? They must be diagonal. Now, D is already diagonal. That means that M inverse L is diagonal because D is. Okay. Now, M and L are unit lower triangular. Therefore, the product is unit lower triangular. So one must Okay. Actually, I want to see if I can cut off some space here. I didn't like it's going onto a new page. Okay, hold on. Okay. Okay, so now I can actually say what M inverse L is equal to. What it must be equal to. It's diagonal, and both M and L are unit lower triangular. So diagonal entries are 1. I thought I heard somebody say something, but I'm not sure. My hearing is awful, remember that.
Is it just equal to D?
Not D.
Identity?
Identity matrix, yeah. It's identity. Because M and L are unit lower triangular, therefore M inverse is unit lower triangular. You multiply them, still unit lower triangular. Diagonal entries are 1. But it's also diagonal because we have upper triangular equal lower triangular. So it must be identity. And M equals L. So we have A is equal to LDL transpose. Okay. So this factorization is more of interest because now these two matrices on left and right are the same because of symmetry. Something we might have guessed anyway, but now at least this way it's been proven. So this is called the LDL transpose, or some people just call it the LDLT factorization, with a T referring to transpose. Okay. Oh, that just sent me onto a new page. All right. So to solve AX equals B with A symmetric, can compute its factorization, LDL transpose, and then solve these free systems. Okay. So first, what you do is you solve L y is equal to b. So that part is no different. In fact, this L is literally the L from the LU decomposition. It's exactly the same matrix. So that's forward substitution. Then what you do is you solve dz is equal to y, and d is the diagonal matrix, so you're just performing n divisions. And then finally, you're solving L transpose X is equal to Z. And that is back substitution. Because L transpose is unit upper triangular. Okay. All right. So that's how you could solve a symmetric system. And I should point out that I won't really go into the algorithm for LDLT here. It's better to use A equals LDLT than A equals LU when A is symmetric. Because the symmetry of, and therefore these two factors being just transposes of each other, leads to the algorithm taking 1/3 n cubed flops. So Gaussian elimination requires 2/3 n cubed flops because you have to compute the entries of L and U both. But here we only need to compute the entries of L and D. The output is literally about half what you would require from Gaussian elimination, where you need both L and U. So it's by trying to compute this as economically as possible and avoiding redundant computations. It could take half the operations. So symmetry will cut the work in half because the number of unique entries is cut in half. Okay. Now, so that's all I'm going to say about this algorithm, except for one other thing, which I've ignored up to this point. What about pivoting? Because if A is symmetric, PA, so P is a permutation matrix, is almost certainly not going to be symmetric. So interchanging rows like you do during Gaussian elimination with pivoting will destroy symmetry. But you can do the following. PAP transpose is symmetric. So in other words, if you swap rows and then perform the same swapping but of columns, so in other words, you're interchanging rows 1 and 3 and then you are interchanging columns 1 and 3, that way you can preserve symmetry. So as long as you carry out any pivoting you need to do that way, then you can do LDLT. So what we have is PAP transpose is equal to LD L transpose. So that's the factorization you end up computing. In that case, you need to be careful to take the permutations into account when solving V systems, just like when you do Gaussian elimination with pivoting. So pivoting is a little dicier, a little more work involved, but still, you're still getting those savings that you get from the symmetry. Okay. But now, for the remainder of the time, I'm going to focus on a subset of symmetric matrices called symmetric positive definite. So symmetric matrix A is positive definite, or we say that A is no, shut up. SPD, so the acronym for symmetric positive definite, if this expression, if this inequality holds, x transpose A x is strictly greater than 0 for any non-zero vector x. Now, if x is a 0 vector, then this expression will be 0. But as long as x is a non-zero vector, this expression must be strictly positive. Now, one equivalent definition, all eigenvalues of A are strictly positive. And one comment I want to make is eigenvalues of any symmetric matrix are real. Eigenvalues of a real matrix of real entries, generally can be real or complex. Just as a polynomial with real coefficients can have real or complex roots. But when a matrix is symmetric, eigenvalues are real. If it's positive definite on top of that, it must be positive. Okay, and those of you who either don't know or don't remember what eigenvalues are, whenever we have this relationship, Ax is equal to lambda x, where x is a non-zero vector, and lambda is a scalar, so it's just a number, then x is an eigenvector of A, and lambda is an eigenvalue.
Isn't lambda just the volume of the transformation?
Oh, sorry, what?
Isn't lambda just the volume of the transformation?
You're thinking of determinant. Yeah, the when you have a 3 by 3 matrix, the determinant of a matrix is the volume of a parallelepiped that has the rows as the
Yeah, I remember that.
direction
I
vector.
just remember there's some relation between the scalar and the matrix.
Because also the determinant is also the product of all of the eigenvalues. So if it relates to that. Okay. So a couple quick things about eigenvalues. The determinant of A is the product of all eigenvalues, and this expression, trace of A, which is defined to be the sum of all the diagonal entries of a matrix, so very easy to compute, is the sum of all eigenvalues. Eigenvalues are nice because what we have over here, A times X, that is matrix vector multiplication, which is a relatively tedious operation. You're taking a dot product of each row of A with X. So there's a summation involved for each entry. Lambda times X is scalar multiplication of a vector, a very simple operation. All you're doing is you're taking all the entries of X and multiplying each one by lambda. So eigenvectors are those special vectors where the matrix vector product condenses to this simple operation here of scaling. So they're very convenient for various things like functions, computing functions of matrices, things like that. I deal with them all the time in my research for solving PDEs that is helped by matrix functions. Functions of matrix like the inverse or the exponential become very easy to compute if you know eigenvalues and eigenvectors. So I won't get into much in this class, but I'm just pointing it out as a alternative definition of symmetric positive definite. There are certain properties of symmetric positive definite matrices. In general, it is not easy to check whether a given matrix is symmetric positive definite. I mean, symmetry is easy to check, but positive definiteness is not. It's really hard to tell that a matrix is symmetric positive definite just by looking at it. Although sometimes you can rule it out. So some properties, besides the eigenvalues being positive, the determinant must be positive, which makes sense because it's a product of all the eigenvalues and they must be positive. All diagonal entries must be positive. So if you have a given matrix, you see it's symmetric, but any of the diagonal entries are negative or zero, but you know right away, bam, it's not positive definite. Okay, and another, the largest entry must lie in a diagonal. So an SPD matrix is allowed to have negative entries in it. They just can't be on a diagonal. And generally not going to be able to have positive definiteness unless you have larger entries on a diagonal and smaller entries away from it. Okay. Also, because the determinant is positive, A is invertible. A inverse is also symmetric positive definite, and in fact, that's one of the homework problems. Is for homework 3 to prove that A inverse is SPD. Okay. Now, so how can we check? Not quickly. Now, you can check the principal minors of A, which this has come before. are the determinants of the leading principal submatrices of A. So to refresh your memory, because this came up when discussing existence of the LU decomposition, this matrix, which I call AK, okay, something went wrong here. Okay. That consists of these entries, so A11, A12, A1K. Okay, A1. Okay. All right, so this matrix here, but it's just, you're taking the first k rows and taking the first k columns of that. So it's a k by k matrix. Are the leading principal submatrices. Okay, the principal minors are just the determinants. Okay, and I'll call these m sub k. All right, so we can say A is symmetric positive definite if and only if all principal minors are strictly positive. Okay, so that would be a way to check if a matrix is symmetric positive definite, but that is not easily done because computing determinants is expensive. Okay. Now, if we recall, if the principal minors are non-zero, at least, then that guarantees existence of the LU decomposition. It means that it is never absolutely necessary to pivot. You would not have a division by zero situation. It might still be advisable to pivot, just to reduce the propagation of round-off error, but you'd never be forced to. So if you have a symmetric positive definite matrix, the principal minors are positive, so certainly non-zero. So in that case, if you're going to do Gaussian elimination on an SPD matrix, you don't need to pivot. But again, because of the symmetry, we can take advantage of that and reduce the amount of work. So we could do the LDLT factorization and know that we don't need to pivot. But I want to show you another factorization. Okay. So if A is SPD, you can compute VLDLT factorization and don't need to interchange rows and columns. But we can also compute what is called the Cholesky factorization, which has this form. A is equal to GG transpose, where G is lower triangular and has positive diagonal entries. So it exists if and only if A is SPD. All right. So what you could do is if you're going to solve AX equals B, then you perform these steps. Cholesky factorization, then Gy is equal to B, and then G transpose X is equal to Y. So if Gy equals B, that's forward substitution, because G is lower triangular, and then G transpose X equals Y, back substitution, because G transpose would be upper triangular. And the cost of computing Cholesky is 1/3 n cubed flops, same as LDLT. So again, because of a symmetry of A, you're saving half the arithmetic operations. Okay. Now, before I go into detail on the algorithm for Cholesky, if you looked at the practice test, you already see there's a problem about it there, and also it's featured on the homework. So if A has Cholesky factorization, and we have A, which is equal to GG transpose, which is equal to LD-LT, and because L is unit lower triangular and D is diagonal, we have a following relationship between the two factorizations. G is equal to L times D to the 1/2, so D is a diagonal matrix, which due to A being symmetric positive definite, D must have positive diagonal entries, so you can take the square roots there. It has to be a positive square root. So the two factorizations are actually very closely related. So for this reason, LDLT is called, as a nickname, square root free Cholesky. Because what you'll see is that the algorithm for Cholesky factorization does require taking some square roots, whereas LDLT doesn't. Okay. All right. Okay, one more comment I'll make about Cholesky before I get to the algorithm. Some sources express the Cholesky factorization differently, like R transpose R, where R is upper triangular. So, in fact, I think a help page for MATLAB's MATLAB has a function called chol, C-H-O-L, that computes the Cholesky factorization. And it will return this. It'll return R, which corresponds to G transpose. It really is the same factorization. It's just different notation used to express it. So I've seen both, and for some reason I developed a preference for the lower triangular form. So that's how they're related. The point is, it's always a lower triangular times an upper triangular. The two factors must be each other's transposes, and the diagonal entries have to be positive. Okay. All right. Okay. So now I'll show you. Whoops. The algorithm real quick, but then we're going to actually carry out an example. Okay. All right. Because I want to point out there are certain similarities with Gaussian elimination. For one thing, we have 3 levels of nested loops. So this algorithm requires a cubic number of operations, order n cubed. And versus division involved to compute the elements of G. It's somewhat like computing multipliers, but not exactly the same. And then this step right here is kind of like the main step in Gaussian elimination, where we're updating entries of A using entries of G. So now, so this is what you would implement in MATLAB. And in fact, one of the homework problems, where is it? Okay, yeah, this one is where you will be implementing this algorithm. But I can show you how you would carry it out by hand, which stepping through this and carrying out each step here would be kind of laborious. But from seeing how the products, how the entries of G can be computed just by equating A to GG transpose, you kind of see how the algorithm comes about. Okay. Now, so now I'll step through an example. All right, so I'm going to make up a what do I have here? Okay. Whoops. Oh. All right. So as I mentioned, symmetric positive matrices are allowed to have negative entries. They just have to be off a diagonal. And also notice the largest entry in a whole matrix, 44, sits on a diagonal, and the second largest entry is on a diagonal as well. Okay. So if I equate this to GG transpose, so this first matrix will be G. Okay. And then the second one will be G transpose. All right, so what I will do is fill in a general lower triangular matrix for G. So G11. All right, and then we have G21, G22. Okay. And then G1, G2, G3. Okay, and then okay. Okay, so that's G, and then we're going to fill in G transpose. Now, one thing I want to point out as I'm doing this, normally, if I'm filling out a matrix like this, the first row, I would have G11, 1, 2, 1, 3, 1, 4. But now I have the opposite, and the reason why is this is G transpose. It's the transpose of this. So these entries in the first column over here should be the same as the first entries over there. Okay, so, and this is going to be G transpose, so that is upper triangular. Okay. Okay. So now what you can do is you can carry out this product of these matrices and equate them to the entries over here. And you can start, basically you can proceed through the lower triangle, starting from first column, then moving to the second, and so on. So for example, hold on, okay. The 1, 1 entry, which is equal to 9. Bless you.
Thank you.
All right. So, okay, too many spaces here. All right. So, A11 entry is the first row of G dot product of the first column of G transpose. So I go across the row and down this column, first column, multiplying entries as I go and adding them up. But most of the entries are 0. So all I have is G11 squared plus 0, 0, 0. So I'm just going to have G11 squared. So that means that G11 is equal to the square root of A11. And we must choose a positive square root, so it's going to be 3. All right. So now we have a 1, 1 entry that's determined solely by A11. Next, we go to the 2, 1 entry. So I go across this row and again down the first column. But the first column is mostly 0. So I'm going to have G21, G11, and that is equal to A21, which is equal to minus 3. So that's equal to G11, G21. Now G11 is already known. So G21 is equal to A11 over G11. So that's going to be minus 1. Questions so far? So it's just matching A against a matrix product. The 3, 1 entry. So I go across the third row and down this same first column. Again, mostly 0. So we're only going to get one term. So the first column is particularly straightforward. So A31, which is equal to 3, that's equal to G11, G31. That should be 3, 1, not 1, 3. Okay. Now, again, G11 is known. So I can say G31 is equal to A11 over, whoops. Got to keep an eye on me. A31 over G11. So 3 over 3, so that's equal to 1. And then finally, we could finish off the first column. That's going to work out the exact same way. So the first column so that's just is always going to work out as just dividing the corresponding entry of A so A41 divided by G11, and that is equal to 3. So first you begin the column by taking a square root of A11, and then G21, G31, G41. Rest of the first column, you're just dividing that column A by G11. That's it. Okay. So now the first column of G is filled in. So in fact, I'm going to do exactly that. I'm going to go, well, actually, I'm going to make a copy of this equation. Okay. All right, so we have 3, -1, 1, and 3. So for those entries we have okay, 3 -1, 1. 3. Okay, and then similar to the first row of G transpose. Okay. All right. So sorry, things are like it puts in this spacing that I don't ask for. Kind of throws things out of alignment. Okay. All right. So now we can move to the second column. So starting with G22, always starting with a diagonal entry because it's lower triangular. So here I'm taking the second row, going across the second row of G, down the second column of G transpose. So I have G21 squared plus G22 squared. So diagonal entries are always equal to a sum of squares of entries of G. So what that gives us is A22, which is equal to 17. So that's equal to G21 squared plus G22 squared. So with A11, we just took the square root of, or G11, we took a square root of A11. Now G21 is known, so we have to subtract that off. So what we get is G22 is equal to the square root of A22. And now, unlike 1 entry, we got to subtract this off. So minus G21 squared. So that's going to be, so 17 minus, so G21 was equal to minus 1. So we get 17 minus 1, 16, so we get 4. Again, take a positive square root. Okay. Now, you can see where taking a square root is risky because we may be taking a square root of a negative number. Also, these divisions may be dividing by 0. However, if a matrix really is symmetric positive definite, none of those things will happen. But Cholesky factorization is actually a good way to make sure that a matrix is symmetric positive definite. If it is not, then one of these operations will fail. You'll be either dividing by 0 or taking a square root of a negative number. So probably is the most efficient way to check, since the other way I've given you is computing determinants, which is also laborious. Okay, so now I can fill in that entry. So I'm just going to get rid of a clutter here. Funny spacing. Okay, so we have 4 there and 4 here. Okay, then we move to the rest of the column, so G32. Okay, so if we look at A32, which is equal to minus 1. So here, we're going across the third row, and down to second column. The second column only has 2 non-zero entries. We're going to have 2 terms. So G free 1, G21, and then G free 2, G22. So I'll fill that in. Okay, so G free 1, G21 plus G free 2, G22. Now, one thing I want to point out, those are the index patterns here. If you look at the row indices, in both cases, free 2, free 2. Well, that's the entry we're going for, free 2. Then look at the column indices, 1, 1, then 2, 2. So those start from 1 and are counting up to the minimum of the indices that you have here. So that pattern we'll see throughout. So now everything here is known except G free 2. Now, when we were dealing with the first column, we just had one division to perform. But in this case, we have to take A free 2 and subtract off a term we know, G free 1, G21, and then divide by the diagonal entry. Now, that happened before. We just have something to subtract off first. Okay. What's it squawking about? Oh, okay. Okay. All right. So now we have. All right. So A free 2 is equal to -1 minus G free 1, which is 1, and then G21, which is -1, all over G22, which is 4. So what happens in this case, we actually get 0. So that is allowed, as long as it's not on the diagonal. Okay. So I'll go ahead and fill that in. Okay. All right, so 0, 0. Okay. And then we go to, then we'll finish off the second column. Okay, so for A 42, which is equal to -7. So we go across the fourth row, down the fourth column. Again, just 2 non-zero terms. So we get G41, G21, plus G42, G22. So again, the row indices match the entry we're trying to get, 42. The column indices start at 1 and they count up. And you get each term up to the minimum index, which is 2 in this case. So then G42, again, we take A42, subtract off the term that we know, G41, so terms from the first column that we already computed, over G22. Okay, so -7 minus 3 times -1, all divided by 4. Okay. Oh, okay. I see what I did here. This is done a little differently in the book. Okay. Okay, so we have -7 plus 3 is equal to -4. So we get -1. So now I can fill that in. Okay, almost there. Okay. All right. So so then for the third column, yes, thankfully there are only 3 entries left. So G33, we go across the third row down the third column. We're going to have a sum of 3 squares now. Like I said, every diagonal entry is a sum of squares. So A33, which is equal to 17 also. So that's G31 squared plus G32 squared plus G33 squared. So therefore G33, we're going to take square root of A33 and then subtract off these other squares from preceding columns, but in the third row. Okay, so we're going to get 17 minus G31 is 1, and G32 turned out to be 0, so we get 4 again in this case. So notice as we go from one column to the next, each entry is taking more work. There's going to be more terms involved. Okay, so 4, 4. Okay, and then we just have this one last entry in column 3. So for free entry, again, across the 4th row down the 3rd column, there are going to be 3 non-zero terms. Okay. All right. So A43, which is equal to 15. All right, so that's going to be what? Oh,
It's supposed to be A, not G.
yes, A. Thank you. Okay. All right, so 4th row, 3rd column, so it's going to be G41, G31 plus G42, G32 plus G43, G33. Okay. Again, the column indices count up from 1, 1, 2, 2, 3, 3. The row indices, 4 and 3, 4 and 3, 4 and 3, that's the entry we're trying to get. So then G43 is going to be A43, and we subtract off the terms from columns 1 and 2 that we already know. Divide by the diagonal entry, G33. So that's going to be 15 minus G41, which is 3, and G31, which is 1. And then G32 is 0. So divided by 4, and we wind up with 3. And then the very last entry, hallelujah, A44, so that is the sum of squares. So G41 squared plus G42 squared plus G43 squared plus G44 squared. And that entry is equal to 44. So G44 is equal to, okay, so A44 minus G41 squared minus G2 squared minus G43 squared. Okay, so 44 minus, so a 4-1 entry is 3. A 4-2 entry is minus 1. And G43 is equal to 3. Okay, so 44 minus 8 is 26. So it's going to be 5, taking the positive square root. So now I can fill in those last 2 entries. So 3 and 5. Okay. All right. So that's Vichelevsky factor. So this times its own transpose is equal to the original A. So what we see is by going from column to column, so first column top to bottom, the second column diagonal to bottom, and going in that order, you always have one entry that is unknown. If you look at the equation for each entry of A being expressed in terms of entries in G, you always know all the entries involved except for one, and then you can go ahead and solve for that one and go from there. Okay. No. Okay. So questions about how that unfolded? So actually these formulas that we have here, you can see they come from matrix product formula. So Aij is equal to the sum k equals 1 to n of Gik times G transpose Kj. But then I can rewrite that as Gik Gjk. And then we keep in mind that G is lower triangular. So these entries are only non-zero if a row index is greater than or equal to the column index. So I must be greater than or equal to k, and j must also be greater than or equal to k. So, in other words, k does not go from 1 to n. It goes to the minimum of I and j. So that's the range of the sum. So if you look at all the formulas that I gave for the entries of G, so really all of these came from that matrix product formula. It's just a matter of in what order do you examine these entries so that you can actually solve for them. Because we see that entries in later columns depend on more entries of G, whereas here the relationship between entries of A and entries of G in the first column are extremely simple. So of course you might as well start with the first column, fill that in, and go from there. Because we see what happens in this matrix product formula. If we're in the first column, so j equals 1, we only have one term here. So you can solve for those entries of G very easily. Okay. Now, okay, we have 8 minutes. Does anyone have any homework questions? Yes.
The rewriting the Gaussian elimination to work for just a matrix.
Yeah.
And no vector.
Yeah.
There's no algorithm for that, right? So you just have to do forward and backward substitution and break it up.
No. Okay, you're going beyond the. Okay.
That's afterwards.
Yeah. Gauss elimination is just the elimination. Like, in other words, from the previous homework that you're modifying at 317, That's the algorithm. So you're not adding anything new to that. If anything, you're taking something away because anything that has to do with B, B being passed in as an input, being B returned as an output, and working on B, get rid of it. The only thing that really changes here is storage, because the previous function would return A where the upper triangle is correct, the lower triangle was undisturbed. But you had no information about the multipliers because multipliers were computed, but they were never stored anywhere. So this is really about storage. That as you compute multipliers, you store them in the lower triangle of A.
So you will have multipliers in this.
Yeah, but you already did.
Like, no.
What? I'm sorry, I can't hear you.
When I showed you the code, you made me take out the multipliers.
I would not have made you take out the.
You didn't take them out, but they were like already accounted for somewhere else. I don't know.
Okay.
I don't have M in my code, but it works.
Well, it may not be called M anymore.
Well, I think it was accounted for in something else.
Like now, because what you're doing really is, like, since you're storing them in the lower triangle of A, then you can use that in place of what was Mij.
Oh, okay, that's what.
Yeah. Okay. So it's still conceptually a multiplier. It's just not called Mij anymore. I mean, you could compute that, and then you store it later. No harm done there, but I don't know if I answered your question.
Kind of. I just have to look at it.
Okay, or we could look at it after or something. Yeah.
I had a related question for that one and question 20 that I haven't really started in full.
Yeah.
Notice in your notes and in the book it says you don't want to store P or L explicitly. So
In other words, as a separate matrix.
yeah, just
Okay.
not seeing what else you need to do in that case.
Okay. Well, first for L, that's what we were just talking about.
Well, like you said stored in A, but then when it comes time to print it or whatever, are you just supposed to just do slicing along?
I mean, personally, I don't care about what happens when it comes to printing it anyway. That is, it really visually is not very meaningful, just because. Okay, you have this matrix where you have the lower triangle has whatever multipliers were used, and then the upper triangle is the row echelon form. Now, here's what you could do is I'll make a note here.
Does it matter if you store it explicitly?
Hold on. Okay. Okay, so this is for. Okay, so sorry, are we still talking about L here, or what I mean by storing L? I'll talk about P later, but storing L explicitly, in other words, as a separate matrix that includes the diagonal entries, because the diagonal entries we know what they are. They're 1, so it's a waste to store them. And besides, suppose you reduce A to upper triangular form, you don't want to store that just a upper triangular matrix where half the entries are 0, again, because it's wasteful. When you look at the entries that are actually of interest, you have an upper triangle, that's your row echelon form, that's your U, and then a non-zero part of L excluding the diagonal. Well, that happens to fit neatly into the lower triangle of A that you were just busy zeroing. So that's why you mash them into one matrix. Now, but here's what you can do. When returning L and U stored in A, if you're looking way to check it, here's what you can do. Okay. So first you can recover. So after your function is exited and you have this A that has L and U mashed into it, you can do. First, you can recover U. U is just the upper triangle of A. So now you have U explicitly. But again, this is only for checking, not for actual computation. Now, as far as L, what you can do is you can make an identity matrix that's the same size as A, so that fills in the diagonal part. Then you can add on to it the lower triangle of A, but use -1 as a second argument. That way it leaves out the diagonal. It takes everything strictly below the diagonal, and now you have L. And so then what you could do is you can check LU should equal A. Now this is for problem 11, so not pivoting. So what you should get is a matrix that the entries may not be exactly 0, but it will be very close to 0, like very small numbers on the order of like 10 to the minus 15 or something like that. So that's how you can recover L and U from what is returned by Gaussian elimination when it's doing the storage efficiently. So this part right here, I call it the interesting part of L, the multipliers. Yes?
So I have questions on 329.
Okay. I still want to talk about the pivoting, but I'll get to that in a moment. Okay, so 3, 2, 9. Okay.
So we're giving matrix L, but we're not giving it B.
Oh,
It's supposed to take 2 arguments.
just make a random B.
So we can just make it random.
Yeah,
So
I mean,
what results are we giving for this? Because making a random B and we don't know the random B I chose. So what am I reporting back?
well, what you could do is you could do L/B to get the exact solution.
So what are we telling you? Because are we just testing the function and seeing if it's working?
Yeah. Yeah, that's all you need to do.
Because you've already written this function.
Oh, sorry, what?
You already wrote this function in class.
In MATLAB?
Yeah, you wrote the code in class.
Oh yeah.
So we're
Oh,
just
I remember now. Okay.
We're just testing the code. What are we supposed
Okay.
I
You know what? I just won't grade this one. Okay. I've given the meat of it away, so there's nothing interesting for you to do. All right, so you get 3 points for that one. It's less for me to do. Okay. Oh shoot! I'm past time. All right. Quick word about pivoting. So instead of storing a permutation matrix P, what you do instead is, in your code, create a vector. It's indices 1 to n. So this vector 1:n consists of all the indices from 1 to n, and then swap indices of. So I'm going to call this lowercase p. Swap indices or swap elements of. Stop that. God, I hate this thing sometimes. Of p whenever swapping rows of A. So whenever you do row interchange, you're swapping like row J with something else, like rows J and Q of A. Swap elements J and Q of P. So that way P is implicitly a record of row interchanges. The only time you need P is for forward substitution. To solve Ly equals P B, here's your MATLAB expression. B of P. That's it. So in MATLAB, passing this vector of indices will automatically return B with the entries from those positions in that order. So that carries out for permutation.
So it's P column vector.
P is a row vector. So indices are generally row vectors. And a colon operator makes it a row. B is a column vector. So B with this vector of indices passed in will still be a column vector, but with the entries in the correct order. Well, we're 4 minutes past time, but of course anyone can ask questions. Or did you want me to look at what do you have? Oh, sorry.
Whenever I get back from
Yeah, that's fine. Okay.
I don't really know.
Okay.
I just took out P. And then
Right.
I'm just trying to figure out what it means.
Okay. Because it seems to be working, or?
No.
Oh.
Well, I haven't actually noticed it.
Oh, okay. All right. Okay, well.
I'll look at it.
Yeah, okay.